Okay, so what we've done is we've measured the size and mass of the first exoplanet that's smaller than the Earth. There are 3 exoplanets at Kepler-138. The innermost one is the size of Mars, and we've measured its mass to be Mars-like as well. But as we were saying earlier, it's much hotter than Mars. The other 2 are both slightly larger than the Earth, and they're a little bit further out. They're also very hot. They're much hotter than the Earth. And they actually have an interesting dichotomy. One, they're both about the same size, but one is probably rocky and is dense like the Earth, and the other one is very low density, so it's probably a mixture of rock and water or gas. So there's quite a variety of worlds in this little system.
The exciting news is that you've measured such a low mass planet that it has a density that indicates it's rocky. And you did it in a somewhat unusual way, or at least a way that we are now getting familiar with, given the fantastic data from Kepler.
Yes.
But this is the smallest mass. How did you do that?
So the Kepler data set is how we do it.
Or either one of you, but I was asking.
Okay, go ahead, Jason.
All right. So to measure the mass meant observing the planetary system for a long, uninterrupted time. And Kepler finds and measures properties from planets from what is known as the transit method. Right? So you have your star, and then if the system is aligned correctly, you will watch a planet go in front of the star, and it will block out a little bit of light. And it's a very periodic motion, at least if there's a star and a planet. As you put other planets into the system as well, gravity is a fairly universal law, so it's going to act on all the masses in the systems. And that will perturb the orbits of individual planets so that it's no longer a strictly periodic transit that you see once per orbit. Instead, it's starting to come a little bit earlier, and sometimes it comes a little bit later. In the case of Kepler-138b, we were seeing transits that were sometimes an hour earlier or an hour later. And it's the magnitude of that effect that then allows you to unravel one of the masses of the other planets and the mass of Kepler-138b as well. I guess we lost Jill?
No, Jill's still here and listening with great enthusiasm. Okay, so you said an hour early, an hour late. This is a pretty small variation.
Yeah, it's a very
in transit timing compared.
Yeah, it's a fairly small effect. I think in the solar system, we see it's on the order of seconds. The transits vary, like the perturbations of Jupiter on the Earth, so it's smaller. In this case, with Kepler-138, the periods are very short and it makes it a compact system. So we're talking periods of 10 days, 12 days, and I think it's 15 days, Daniel. And it's together that they make those resonances, and then we start to unravel the mysteries and measure the masses.
I'll just add that part of being able to do this is the Kepler data set. The variations are, for the inner planet, they're about an hour, and for the other 2 planets, they're 10 minutes and about 45 minutes. But we can measure the time of the transit, the exact moment that it passes between us and the star, to within a few minutes. So because we can measure it so precisely from the Kepler data, we can get this information about how the planets are interacting with each other with their gravities.
Daniel, I was really intrigued when you said it's a hot Mars. When you're looking at our solar system, a hot Mars is the Earth, right? But we're talking about something that's 400 F. Or 500 F. So it's more like a hot Mars or a cold Venus, or
maybe even Mercury.
Even Mercury.
Yeah, in some ways it has more in common with Mercury. It's small, it's hot, so it can't retain an atmosphere, and so it's just a rocky, small world, different to Mars, right? Because Mars is cold enough that it may have had water at some stage. And it probably took some time for Mars to lose the water. But this is close to the star. It's about 320 degrees Celsius. And so it's too hot for life as we know it.
No, yeah, but can you imagine a really hot world with lava or with some volcanism going on? Are these the kind of things that you are envisioning? And once again, remember, Mercury might be very close and very hot to the sun, but there are still traces of water and ice in the past. So these are really completely different beasts. This is expanding so much. Mm-hmm. The gallery of planets that we are thinking about when we are talking about planetary systems. You are talking about a Mars-sized, Titan-sized world that is basically a big rock ball.
Right.
So it's a very, very large moon-like environment, most likely.
Yeah, and it's likely to be tidally locked to the host star. So one side will always be facing it and get highly illuminated and probably to those large temperatures. That the dark side, it's going to be very cold, right? If there's a lack of atmosphere on it, you're going to have unmoderated temperatures. They will quickly drop below zero, right? 0 Celsius in Fahrenheit. So there's even potential to hide ice behind the moon. Of course, it's all skeptical as far as we're concerned.
Yeah. So basically, to summarize this, you can say it's a Mars-sized, Mercury-like planet.
That's right. That's our first step at it. Yeah.
Yeah, that is right.
So I've got a question for you. How far have you pushed these transit timing variations as far as they can go for this system? Can they tell you about maybe a fourth or a fifth planet farther out? Is there anything we can say about the possibility for planets a little less toasty?
In this case, it's probably about as much as we can do with the Kepler data. It would be lovely to get more transit times from other missions, from telescopes that continue to monitor this the stuff from either the ground or with the test mission, NASA's test mission. But we don't think that there is a fourth planet in there that is causing the transit timing variations that we see. So the variations that we see in the orbital periods of the planets, they vary over a 4-year period, and it kind of matches up with what we'd expect given the planets that are there. If there was a fourth planet in there that was causing the changes in the transit time, that would actually confuse our mass measurement, and we would have an inaccuracy. But we're confident that if there is a fourth planet there, as long as it's not close to resonance with one of the planets, it's unlikely to affect our measurement of the planet masses.
I like to think about it in terms of even the discovery of Neptune. Right? Neptune was discovered originally by looking at the motion of Uranus and noting that it wasn't following the Keplerian motion as predicted by the rest of the planets that we knew about. So people quickly realized that there must be an additional planet that's further out that's causing perturbations on Uranus, and that was the discovery of Neptune. So if we had seen perturbations in the transit timing variations that we measured from the Kepler-138 system, then we would have pointed towards another planet. But as Daniel's alluding to, not knowing about that planet further out because we would be unable to get any information about it because it's too far away to directly image, we wouldn't be able to get real velocities, would have introduced a lot of uncertainty into the measurements we have. So we're not seeing evidence for planets further out, but it doesn't mean that there are no planets that are further out in this system.
Okay, so that's important for me because we've been using the Allen Telescope Array to look at the Kepler detected planets and candidates to see if we can detect any evidence of someone else's technology. And so far with Kepler-138, I mean, you guys have discovered so many planets we can't keep up. So with 138, I think we've gone through about 8% of the total frequency range. And I guess we should keep going if there's a possibility that there is a planet farther out that hasn't yet been detected.
Absolutely. And it doesn't have to be that much further out than the outermost planet, Kepler-138b. Kepler-138d is around the temperature of boiling water on Earth. So if it was just a little bit further out, it could have liquid water. But it's probably too hot. But there is a fourth planet out there. It would probably be in the habitable zone if it's not too much further out than the 3 planets that are transiting.
I was waiting for Joe.
I'm Yeah, I'm sorry that the internet connection here at the hotel is not actually holding up to what we need. I chose to do it in my room where it's quiet rather than downstairs where it's chaotic, and maybe that wasn't the best choice.
It seems to be working well now.
Okay, and you see that picture from Australia and days ago, years ago, probably more attractive than the real thing. So what other kinds of tricks, not really tricks, but science can we pull out of these 14 quarters of Kepler data which have the unique, at least unique to date, characteristics that they've been continuous? That's a very, very long continuous data set. We can no longer get that kind of continuity with K2, and TESS is likely to be shorter lived than those data. So are there some more bits of science to be pulled out of these long, long data sets?
Yeah, I think for sure. There's information about the host star itself. We know our own sun goes through very active solar cycles on many year timescales. If we're going to have distant worlds around their stars, we'd like to know how their suns behave over time. If they behave like our own solar system, that helps to put us in context. The other part is that in terms of transit timing variations, Kepler-138 is a little bit of the low-hanging fruit because it's the planetary systems with short orbital periods and these compact nature that allow us to see the TTVs right away. But now we can go back to Kepler and we sort of know what we're looking for, and you can start to play the same tricks and tease out other mass measurements of other planets around other stars and start to fill in a more statistical distribution of what planets are like around a whole variety of conditions and types of stars. So it's really expanding our knowledge. It really is. It gets used way too much, but it's really true. The discovery of 138b C and D and its masses is really the tip of the iceberg as far as we're concerned for learning about the nature of mass and radius relationships for exosolar planets.
And does that help you to actually look for planets that are theoretically of smaller size than what Kepler was originally designed to find? Now that you know how to play with the motions of this planet and trying to infer that there is another planet out there, so maybe it's an indirect way of looking for a smaller thing than you originally were planning to.
Maybe. I think Daniel's our dynamics expert, so I'll let him weigh in here a little bit.
Well, let me first say that the more planetary masses that we measure from the Kepler dataset, and the more varieties of stars that we study with planets around them, the more we can try and understand why our own solar system does not seem to be the typical system. There seems to be a lot of these planets that are between Earth and Neptune size that we see in the Kepler data. And as you say, there are probably a lot of smaller ones that are just too small for us to detect in even Kepler's dataset. Kepler-138b is one of the smaller ones, and we're lucky that we can measure its mass. How many that are smaller than the Earth are in the data set, we still don't know. It would be great to analyze the data further. If there are planets, if there are multiple planets in the system, like in Kepler-138, and their orbital periods are changing, that would make them harder to detect, because they have a weak signal anyway because they're very small. And so what we like to do to discover these planets is to fold the light curve, or to stack the light curve of each transit on top of it to build up the signal so you can see the dip in the light curve more accurately. But if the actual time of the transit is shifting because the orbital period is changing, it's harder to find those planets in the light curve. So they could be there, but they're harder to find.
Yeah, the reason I'm asking is because being a geologist and touching things, you with the Kepler mission and future missions are going to allow us to start having a mental picture of worlds that we don't have around here, that we don't even know exist, and start figuring out what type of environment is life possible, what type of life, and all of a sudden this is augmenting and broadening our view on the range of potential zoo land that it's out there for life to be, and life that we know of or life that we don't know of, but we will be able to start theorize about. Mm-hmm. So to me this is absolutely fascinating, and this is why I'm asking, what's the range, and can you tease out the atmosphere? I know we are able to start to be able to do that. Is this a puffy world? Is this a rocky world? How big it is? How hot? How cold? How far away from the planet? How much activity the sun, their sun, has? All of this is giving us so many precious clues to start thinking about things that we are not even envisioning right now. So this is absolutely fascinating.
Yeah, one of the big discoveries of Kepler, just in
so Nathalie, a little.
Can't hear you, Jill.
So Nathalie, a little earlier, Nathalie, you mentioned the possibility of volcanism on this Mars mass planet. Age, I know it's in Lyra, old this system is. I mean, because we're trying to figure out how big a planet has to be in order for it to be active, geologically active, which we think is necessary for life. Mars doesn't seem to be active anymore.
That's debatable.
Yeah.
That's very debatable, especially with the methane discovery. We know for Mars, for instance, that you still have traces of active volcanism as late as a few million to a few 100,000 years ago. So, this is a volcanism at the time scale that we see on Earth as well. For some of the volcanoes that are still considered active today, they are dormant, but they are not extinct. So you can't say that Mars is not active anymore. It probably is. The methane is confirmed, and I think, I would doubt that it's rover related. I really think that we are seeing something. It's hard to tell whether it's volcanic or biologic or both, because life tends to go to places that are hot, that have water, so it might be just an oasis over there. Mars is the size of that planet, did have active volcanism. What's important as well is tectonic activity and the magnetic field. Mm-hmm. And so tectonic activity, plate tectonic activity or may have started on Mars. We have the stripes on the crust on the Martian crust, and you have magnetic stripes that seems to indicate that something happened very early on, between 4 billion years, but it stopped at 3.5 billion years ago because that planet cooled down very quickly. Mm-hmm. So now you put Mars much closer to a sun. I don't know what's going to happen. What I know is that if one face is locked towards that sun, it's going to be really hot, and you might have activity in terms of molten rocks, like you see on Mercury. You have mare, like on the Moon. For me, it's really hard to tell, but the size of that planet, if you're talking about tectonic activity, there was a start of tectonic activity on Mars early on.
You're also going to get a lot of heat sources from tidal energy. Absolutely. That's going to be important, because it's not only very close to its host star, so the tidal energy is very large, which is circularizing the orbit. You also have the perturbations of the other planets on top of it, and it might be still very active. We don't have a good indication on the age of it. We get the ages of planets based on their stars, and it's a cooler star. It's a 4,000 Kelvinish M star, and those stars do not like to tell us how old they are. They're very vain. So as far as we're concerned, this could be anywhere between maybe 1 billion years, maybe as old as the universe. We really don't know, right? It doesn't want to say it. But because of all the additional energy sources, that if you want to envision some sort of hotter world that could allow tectonics or volcanism, probably the tidal input is enough to do that.
I think so too. And this is extremely interesting because at that point there is no way, depending on the period of the other planets around and the period around the sun, there is no way that this little world is going to be able to stabilize ever.
Right. Yeah.
So at that point, it becomes the other way around. Obviously, this is not a world where you think you would find life as we know it. And it's not going to be stable enough for the kind of life we know of. But once again, this is as we know of. And I've seen so many things and heard so many things that, all bets are off for me. I want to be proved that there is a place, where life cannot be.
Well, if this is a very active world and it's continuously outpouring gases from its interior from volcanic processes, maybe it'll turn out that we could use future instrumentation to tease more observations out of what's going on.
And that would be my next question, because when you have a world the size of Mars, although Mars was not very good at keeping an atmosphere, it still has one, a tiny one. And if we have an active world with volcanism releasing gas in the atmosphere or outward in space, is there a way we can tell if it has even a thin atmosphere?
I think it's going to be tough, and even with future representation, maybe. But the fact that it transits means that starlight's passing through whatever comes out of the planet.
Mm-hmm.
It's going to embed its signature in any stellar spectra that we might observe. So if you could imagine you had some gigantic, 30-meter size telescope that's coming sometime in the future, and you aimed it at this planet, maybe you could see outgassing from the planet in the spectrum. I haven't sat down to do the calculations.
Yeah, you have to subtract the star spectrum and see what's left. Right?
But the exciting part is that we are building a 30-meter telescope, which is probably on the order.
Well, actually, not today. Construction is still impeded.
Yes, there's political issues and monetary issues, but it's on a horizon. I'm optimistic that we'll get to the 30-meter telescope regime.
Yeah.
So Daniel, you're the dynamic specialist. Is there any way of looking at the current orbital parameters and deciding whether these planets actually formed in their current orbits or whether they migrated in? And how stable is this system? Is it going to last another billion years?
So at the moment, the system is stable, but we don't know how it formed. It's typical of Kepler's multi-planet systems. We didn't expect to find so many systems of planets that are just so close to each other. They're just stacked in lots of planets, like within Mercury's orbit of their host star, and they're stable. Their masses are low. In this case, the planetary masses are all fairly low, so it helps keep it stable. But how they formed is a very good question. If they are rich in water, and the outermost planet has a low density, they would have had to have formed further out where water could condense when they were forming, and they would have probably slowly migrated in to form their configuration as it is now. Not an easy thing to do without having things crash into each other, because things can go unstable when planets are migrating, and you're fitting them into such a small space. But if they formed where they are, the low density of the outermost planet is probably just due to gas that it's retained from its formation. So if we could look for, with a 30-meter telescope or maybe something, maybe other telescopes, water in the atmosphere of the outermost planet, that could possibly tell us if this thing formed further out and migrated in, or whether it just retains gas from its formation. So we don't know exactly how these planets formed, and it's one of the big questions for exoplanet science. How did these compact multi-planet systems form? And is our own solar system some kind of exception to the rule, or just how common is it that systems like ours, which seem logical to have the terrestrial planets out to Mars, out to where water can exist in liquid form, with very little water. Most of the water in the solar system is in the planets that are beyond the asteroid belt. That seemed logical to us before we discovered all these planets in the Kepler dataset, which are rich in volatiles like gas and ice, but very, very close to their host stars.
Okay. Lee, I can't see from here whether there are any questions from anyone who may be viewing this.
I'm checking right now, Joe. I don't see any questions right now.
Okay.
We're doing a great job answering.
Yeah.
All right. So I think this is a really exciting opportunity. I love the fact that Nathalie was wondering what would happen with a hotter Mars, and somewhere in the cosmos that experiment's being done right now. And if we develop the instrumentation to be able to tease out the physics, it's the way we get to play this game as astronomers. We can't go into the lab and tweak the parameters the way a physicist can. But we just have to find other examples in the universe where the interesting experiment's been done. And I think the one thing we can say about, as Daniel has done, about the study of exoplanets is that there are a whole lot of different ways to make planetary systems. We don't yet know how many ways there are to make habitable worlds, but it's a really fascinating and exciting time.
And I think we have the statistics on our side when it comes to, diversity possibilities.
Mm-hmm.
And but once again, it is so good for us who are used to watch and touch and build the hypotheses and the theory around what we see and touch, to have that data that is being acquired directly or indirectly and give us a broader perspective on what could be possible. The other extreme of that thought is that, yes, the statistics is with us, so anything is possible, and anything we can imagine is going to happen and is being, at the present time, happening somewhere. So maybe we can start, just taking a piece of white paper and just thinking at the most absurd world you could think about, and try to infer what type of life, what type of habitat could be present out there. But this little world here, as I said, Mars-sized, Mercury-like, is very fascinating.
Mm-hmm. I think it's only...
And we're definitely getting closer to finding sort of Earth-like planets in the habitable zone by being able to characterize planets that are very low mass, that are far enough out that they don't really affect the star's motion enough for us to detect them with radial velocities. But we can measure their masses even though they're a bit further out. Really enables us to push how far out we can measure low-mass planets. So we might be able to push the boundaries further out towards the habitable zone.
And if you extrapolate low-mass planet to a moon, do we have any capability of finding moons that might be habitable, such as the worlds like Europa in our own system, or Titan?
Actually, this system, Kepler-138, has been the subject of a study to look for moons in the outer two planets. And using a similar technique, looking for variations in the orbital periods and also variations in how long the transit event was for the planets. And they didn't find moons, but it means that moons are not out of the realm of possibility of what we can look for in transit data. And so moons, in theory, could be more habitable than some of the big planets that we find in the Kepler data. If they're out in the habitable zone, but they're too much like Jupiter or Saturn to be habitable themselves, if they do have moons, that would certainly increase the possibilities of having worlds with life on them out there.
I think one of the things that surprised me is we haven't found large moons around any of these planets that are close in and small. Like, we have all these compact multi-planet systems, Earth-sized planets, Mars-sized planets, but we don't see ones that have moons around them. You don't see double planets, for instance, like twin Earths going around each other, right, in their orbit. Whatever reason, solar systems don't like to form them. Moons seem to be much smaller or non-existent in these close-in, packed-in systems. We haven't really done much investigation for the planets that are further out, where in our solar system we find moons are much more common, per se. Mm-hmm. But so we don't really know much about that yet. But as far as all these ones that are close in, we really don't see that type of activity yet. It's kind of surprised me a little bit.
Well, does that say something about these planets' ability to clean their orbit at the time they are forming as well? Because they are a little bit bigger than the Earth. They don't have to be the size of the Earth, but let's assume that they were the size of the Earth, but they clean better their orbit.
Partially.
Yeah.
Like I expected, Daniel was touching on this, that say 138d has water, which means it formed further out. Somehow it needs to migrate inward and then stop. And part of that is from in the solar nebula of dissipating gas and opening gaps and migrating. But the other process is planet-planet interactions, which can be a much more violent process. And for me, I'd feel almost like that would be a natural way of forming moons. But we don't see them. Maybe we're not looking closely.
But maybe, Jason, the moons are stolen. Maybe it's really hard to hang on to your moon if you've got so many close.
It's a good question, but we don't know. There's a lot of variety in how many moons planets have in our own solar system. Pluto is the nearest thing to a double planet, where its largest moon and Pluto are sort of similar in size scale. And the Earth and Moon come second. So the moon, our moon is much too small to be habitable or to be able to retain an atmosphere. And it's the second biggest moon there compared to its host planet in the solar system. So it seems to be rare in our solar system that moons can be as big as the planets or to have double planets. But it does exist in the case of Pluto. Why it seems to only happen in the outer solar system and seems rarer in the inner solar system, it's a great question. I'd love to know the answer.
So there is a question from people watching out there. Looking at, do you need supercomputers to look at all this data?
Do we need supercomputers to look at all this data? Parts of it, yes. Kepler observed 200,000 stars for 4 years. And every one of those 200,000 stars, it observed every single 30 minutes, or just about every 30 minutes. And for each of those, we observed many different pixels, because it's a camera. So when you download all that data, it's an enormous data set, billions and trillions of numbers, that you need to then process through all our machinery, that we then turn into a few numbers in the end, right? Mass, radius, period is the essentials, right? For part of it, supercomputers were used. For instance, the NASA Ames Research Center contributed the Pleiades supercomputer, one of the fastest computing networks in the world, in order to process Kepler data. And then, of course, doing all of our calculations of the n-body simulations, of gravity simulations, to tease out the masses, also involved a lot of computations that involved more than just your simple laptop, of using clusters of machines to do multiple calculations to both study intrinsic errors and to make sure we were getting the right answer in the end. So yes, large computing is a big part of astronomy, and it's going to become much more essential in the future. I think that it's not all science.
But Jason, one of the things that the Kepler team has done, which I think is so amazing, is that you've made all of the light curves that you have created available publicly for people to investigate, and it is a very vibrant citizen science project now, not to do transit timing variations, as far as I know, but for finding other transits that have been missed by the automated surveys, and there's certainly several examples of that.
Well, I agree, and in terms of the citizen science effort, some of our extremely brilliant public scientists have been able to find transit timing variations on some of the Kepler systems themselves. It's incredible to see what people are able to do with the light curves, as you mentioned, that Kepler has been able to produce and make widely available to whoever wants to go into the Kepler data set to take their own turn at trying to do interesting science with it.
So there's another question here, and I apologize if you already answered this, but how can you draw so many conclusions from such a small eclipse from a distant star?
Can you repeat that question?
I'm going to try to paraphrase it. So the question is, how can we learn so much about these distant planets from tiny transits, planets so far away?
Okay, this star, as Jason was explaining, this star has been monitored every half an hour for 4 years. In fact, for this star, for the last 1,000 days of the Kepler mission, it was monitored every minute. There are 88 million brightness measurements of the star, and it's an incredible amount of data. We found with the TTVs that you need all 4 years of changes in the orbital periods, the transit timing variations, in order to get a good measurement of the masses of all planets. So I can't think of another example of anything in science, or an analogy outside astrophysics or physics, where you would need 88 million measurements of something in order to learn something as precisely as we have. So we've learned the masses of the planets from the transit timing variations. And there's additional data. Telescopes have taken high-resolution spectra of the star, and we include that in our models to understand the star itself and how big the star is. Every time the planet passes in front of the star and dims a little bit of the starlight, it's a measure of how big the planet is compared to the star. But if we don't understand how big the star is, we don't know how big the planet really is. But with the Kepler data, as well as spectra and some modeling of the star, we get good measurements of the star itself, its size and its mass, and we use that to get mass and sizes for the planets. But there's a lot of data that goes into it, and yes, the transits are very small dimmings in brightness, but with millions and millions and millions of observations, we can begin to infer things like the mass of these distant planets.
I like to try to think of it in terms of our daily commute to work. If you arrive in a new city and you're trying to get from A to B, you don't take the most efficient way. But when you're doing that trip every single day, you quickly figure out which the best way. And you also start to see patterns in your commute. You'll say, oh, Fridays, if I leave a little bit earlier, I get to work a little bit more conveniently because of weekend traffic. Or you know there's a holiday coming up. Or you notice a difference in summertime when all the kids are out of school. Right? So all these things are coming to play. With Kepler observing continuously, we're also being able to tease out the patterns from the transits going around into interactions to be able to learn that information. So it's only from long-term observations that we can piece together this puzzle, not just from simple snapshots. Right? The same way that, again, if you just show up in a new city, to get from A to B, you have to do it many times in order to figure out the most efficient route and learn how traffic behaves. And we do the exact same thing with distant extrasolar planets.
So basically you are having rendezvous with planets and stars every day.
That's right.
So, Lee, if that's it for the questions, then perhaps it's time to wrap up and say thank you to Daniel and Jason for sharing this new paper with us.
Thank you very much.
And thank you to Nathalie for some insights into what a hot Mercury-like Mars would be.
Very intriguing.
This stuff is just going to get better and better. I've been involved with Kepler from the sidelines for a very long time, and we're doing things, you're doing things, the citizen scientists are doing things with the data that I am sure none of us anticipated in any way, and I think it's superb. So onward to smaller planets and more Earth-like worlds, perhaps.
Thanks.
Agreed. Yeah, thank you very much.
Thanks.
Yeah, thank you.